Okay, so this is about a joint project, very recent, with Rafi and Dick Lipton. And it has the very ambitious subtitle, Using the Uncertainty Principle to End Malware. So hopefully I convince you that we can keep the promise in the next couple of minutes. Okay, so the problem we'll be looking is malware injection. What is malware injection? We have a system that's running some software. We have an attacker that is trying to inject some malicious software in the system, right? The malicious software, when it starts executing, can do all sorts of bad things. It can take control of the system, write its data on an untrusted server, everything. And we want to see how we can protect such a system. So actually, your computers and smartphones do have mechanisms that protect against such systems. The standard mechanisms are antivirus, firewalls, and security patches. And they work, don't work, you can decide whether this is the case, but what I can for sure say is that for them to be effective, they need to know the virus. So first the virus needs to be analyzed, then we can protect against it. And that has a big issue, which is that the virus might stay on the system for way too long and do damage slowly, which was, for example, the case with the Target attack last year. So those are not the only suggested approaches. There are more kind of research-oriented or experimental approaches that have been suggested in the applied security research. So these are roughly, I'm sure I'm forgetting something, but the most, in my opinion, prominent and most related with our work are software diversification. Here the idea is that we kind of randomize the binary of the software so that when the virus attacks, he will introduce an inconsistency, and that will provoke a system failure. Another one is analyzing the logs and looking for patterns that would not be in the normal program execution. And the one which is probably closer to what we do is so-called attestation. I will say a few more words about it in the following. What I wanted to say here is that although those are more research-oriented, they do have some intuitive security guarantees, but usually the assumptions are either not that well defined or too strong, and they don't have a security proof because it's not accustomed there to do security proofs. So the closest thing to a security proof is finding all possible attacks that I can and show that my system resists these attacks. And then I run it on my computer, and it indeed works, and it seems not to be, I cannot attack it. And to make it more evident that my system is secure, I run it to other computers, and I cannot attack it there either. So that's the closest thing. I'm a bit unfair with it, so let me just put things a bit more in perspective from our side. So I would say that the mode of operation in applied security is I give you a system that works, and it has a chance of being secure. Our mode of operation is I give you a new, very cool idea, which is secure, and it has a chance of working at some point.
Works on paper.
Work means in practice.
Yes, that's what. So we're going to try to live here with security, but I think that at the end you'll see we live somewhere here, and we will shift towards there slowly. Okay, so a bit more concretely now, a bit more theoretically. What's the attack model? This is assume that this is the system memory that we have. Those are, let's say, like binary words. And the virus is another binary consisting of, let's say, 5 words here. And it goes and sits on the memory. And when the sum of the location executes, then the virus kicks in and does all sorts of nasty things. So our goal is to try to detect such an injection. Again, we don't try to protect against it. We won't solve it. But we will try to detect it. And we won't care what the virus is. We need to know what the virus is. So how can we do that? Surprisingly, our idea is inspired from quantum physics, and in particular from that gentleman here. Does anyone know who that is? Too many people were in the boot camp. Okay, yeah. This is Werner Heisenberg. And he has his famous uncertainty principle, which very, very freely interpreted says that when we observe a quantum system, we inevitably change its state. So along the same lines, the principle we're going to be using is that when the attacker injects malware on a system, he inevitably changes its state, and we're going to use exactly this fact to catch him. So on a very, 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 and put as many very as you want, high level, here's what we do. So don't ask me for details here. I'm going to give details in the following. I want to give you the general idea of our approach. Assume that this is the entire system memory. And assume that we have a software that we want to secure. So that it's running the system. It cannot be attacked. So we can detect attacks. So what we do is we take a secret key and we split it. We secret share it. We know this is in crypto. In many pieces, and then we blend the actual software that we want to protect with the pieces of the secret key and write it into the memory. Now, when the virus attacks, he goes and sits somewhere in the memory, and how are we going to catch him? By periodically querying the system with a query which depends on the secret key and needs the entire secret key for answering. And the system will not be able to do so because the virus will have sat on some information which is relevant for the answer. I'm sure you have tons of questions. Just wait 10 minutes for asking. Because, okay, so one question I can already answer is that, of course, this assumes that the virus does not know the secret key or the source of the key, because otherwise it's very simple to answer, right? You just know everything and you reply. I will answer the rest of the questions hopefully through the talk. If not, please ask me when I give more details on the construction. Now I would like to say something about related literature. Yeah, go on.
There is the system that checks the shares. So it's a beautiful application of secret sharing. This system that check the shares is also may also be under attack.
That's an excellent question, and I'm going to answer it. Yeah, this is one. So any question I'm going to answer is excellent. So.
Of course.
So okay, so a few words about related literature. Okay, the problem is huge, right? So everyone understands it, and although in crypto we haven't looked at it too much, in security there's tons of work. So I could spend the entire talk, just giving related literature. Instead, I choose to do what they do, at the end of the movies and give credits like this. If you did not see your paper cited here, let me know. And I will discuss without giving citations because, again, I would have to fill the entire slide. The most related in this security literature line of work, which is the so-called attestation. What is attestation? We can think of it as a challenge response protocol between an interrogator, which we would call the verifier, and a system that we try to verify or interrogate for integrity to see that it has not been attacked. And in a challenge response protocol, the challenge corresponds to something telling to the system, show me that you haven't been attacked, and the response is evidence that this is the case, right? There are roughly 3 types of attestation. Completely software-based, hardware-aided, and what is called remote attestation, which I consider as something between the software and the hardware. And I'm going to give you some general overview of how software-based attestation works to see the type of assumptions that one would need to do for it. Okay, we have the verifier in the system. What happens is that at time t, let's say, the verifier sends to the system some checksum computing function. This would typically be a hash function and a code of evaluating on its memory and the seed. And then the system is, let's say this is the contents of the memory of the system is expected to compute this hash function iteratively, accessing random memory location, and do it so many times that he, with high probability, traverses the entire memory. And he produces a checksum of the entire memory, which he sends to the verifier, and let's say that the verifier receives it at time t prime. So now what the verifier does is, first, he does everything by himself, so he knows the exact state of that system here. He does everything, this will not be the case in our system, by the way. He does everything by himself, computes the checksum and checks that it's the same as the one he received. And the other thing that he does is he checks that the time it took for the system to reply is the time that the system is supposed to take when it has not been infected by malware. So what's the advantage of this approach? No secrets, right? No keys, no nothing. I can really do it on software. there's a lot of drawbacks, which hopefully you're already wondering about from my previous point, which is I really need to know the exact configuration. So the configuration of the system needs to be extremely simple, and I need to know the exact configuration so that even if the malware just does a swap operation while computing the checksum, I observe a detectable slowdown. Furthermore, although there are no secrets, there needs to be a secure channel to the system, right? Because if someone can get the checksum and bypass the secure channel, he can just do the computation by himself. The state is public. Another assumption is that the attacker cannot have external help. Again, this would violate kind of the timing. He could just take the checksum, send it to a much faster server doing the computation, and then return the outcome in time. Then the network delay needs to be predictable. So if there is an unpredictable overhead that the network might take while transmitting that checksum, then I cannot really use the value of the time to say that the virus was there. Another negative, I will go to this one and then lax to this one. Another negative is that the actual checksum code needs to be minimal. So this means that there should not be any way of computing the function that I gave to the system to compute faster than the program I chose. I don't know of any way of proving such a statement. But again, the difference is that there is a system which has been shown to work, under these assumptions. Under these assumptions.
Speed of operation compared to the virus moving inside.
It's not only the assumptions on the speed, it's assumptions on the knowledge of the speed. That's where it gets a little bit less realistic. If it would be just about the speed, it does make sense. But knowing exactly how much time it takes for a system, I mean, there's no way you can know that for a laptop, and that would be my point here. So that this mode of attestation cannot be used to interrogate from a remote location, for example, over the internet, and cannot be used to interrogate complex systems. So you can kind of interrogate your mouse where you're physically next to it, so the network has almost zero latency, and it's a very simple circuit. You can interrogate, your fancy, water kettle if you have a network to it, and you want to see whether it's been infected by malware. Yes, always. But it seems relatively hopeless to interrogate like smartphones, laptops, or even like a computer that sits on your basement for 10 years. It's probably too complicated for that. Furthermore, another disadvantage is that the verifier needs to work as much as the actual system, right? I need to compute the checksum myself, which is something that we in crypto know that, or believe that it's not a good idea. Okay, so this is for software attestation. Very quickly, what is hardware attestation?
Questions now? Can we ask questions now?
Yes, absolutely.
So, are we assuming that during the normal execution, the memory doesn't change at all?
Yes, and we're assuming even more. We're assuming that I know exactly the contents of the memory. The verifier knows, not we, they.
And it never changes.
Yes. This is, yeah. The verifier work can be done offline, absolutely, yeah. I mean, you know your challenge and you know the code, so you can do it offline. But you need to do it, and you need to do it for every challenge, right? Because the challenge needs to be random. Otherwise, once you have answered it, the adversary can answer it again. So you need to do it every time you interrogate. What does offline mean? Like between two interrogations, is it offline or online? Yeah, that you could do, yeah. So attestation can be done also in hardware, not surprising. What we mean by hardware attestation is that we pretty much have a trusted party on board that does the work for us. So this means that the system has an onboard secure coprocessor, a chip, which is it keeps private keys. It cannot be tampered with, and it does complicated crypto. It computes signatures, it computes hashes, it does whatever. It's our dream ideal functionality. So, whether such dream ideal functionalities exist in practice, there are several disadvantages which we can discuss if you want, but one of them would be that this would need to keep long-term keys. What happens if the key leaks? There's also...
This criticism on all crypto. You are criticizing the entire field of crypto.
Why?
Long-term keys.
No, SSL doesn't, I mean, you can, but here the assumption of long-term keys is crucial, right? Because in crypto, you could in principle update your key. Here you shouldn't update your key, because if you do, then you create an attack surface. You know, if you update very often, then the virus will just attack this process, right? So you should rely on something in there, which is the case in modern TPMs. Like really put a key in there, and they almost never update it.
Yes, before the end of your talks, there will be some technical stuff. Because I mean,
but
I think it just would be unfortunate if you don't get the technical stuff.
I plan to be. So I mean, I have a lot of technical stuff in there, but unless you see what's done, I don't think that you'll be able to appreciate, you know, why this thing. There won't be obfuscation or non-malleable codes or, you know, NISCs or snark. There won't be such things. It will be really, really simple crypto. So I don't know whether, you know, the technical is. So there will be very, very, very simple technical stuff. So the goal here is really to make something that works. So I need to compare with things that work. And I assume that I didn't know when I started this project. I assume that people here don't really know how these things that work. Okay, so remote attestation can be thought of as a hybrid between hardware and software attestation. See, it's kind of hardware attestation with very, very minimal hardware assumptions. So I just have a private storage, maybe some read-only memory, and most of the requirements are pushed to the architecture. Most of the schemes still need this code minimality assumption, but I think this is the most realistic mode of attestation. Still, it's, as far as I know, only applicable to very, very small systems, like embedded systems. Stuff that I showed before, like a mouse, or maybe more than a mouse. The advantage of both those approaches is that you can actually do them remotely, right? There are keys. You have private storage, so you can do remote attestation. Okay, getting to stuff that Evgeny will like more. There has been also in crypto works that would in principle try to address such a problem. One which is between crypto and security like ours is the proofs of security erasure, where the idea is that I send to the system a seed, and I expect the system to fill up the entire memory with pseudo-random noise. So it overwrite everything and show me the pseudo-random noise so that I can know that it did so. This is kind of too evasive, but it does give us what is called in security a root of trust. So it does give us something which we know doesn't have malware, but we know that it has, you know, garbage though. It's not clear how much we want that. And it's actually very slow as a process, you can imagine. There are proofs of retrievability. There, the incentives are very, very similar, right? Where I'm trying to, if you want to interrogate a system, to prove to me that my data have not been altered. The main disadvantage here is that it's pretty good when I try to do that on data. When I try to do that on computation, which needs to update, that's not good, because first of all, I need the verifier and the system to be online. And even more, in its update, I need something like, I think the best that we can get is a polylog computation. So that's not acceptable for our purposes. Of course, there's program obfuscation, right? I'm pretty sure. I don't know whether it's been solved. If it's not been solved, I'm sure we solve it in the next couple of weeks. Like I'm sure that the problem can be solved with program obfuscation. It's like it seems like a prototypical application. For the same reasons as the diversification, the thing that you're trying to attack makes no sense, so it's very unlikely you will attack it in a reasonable way, but I don't know. I believe that it can be done. I haven't looked at it. I just put it there because I don't know whether it's been done already. So finally, very recently in this year's PKC, there was a paper about tamper-resilient and leakage-resilient architecture, which is even closer to what we're trying to do. The issue there is that their goals are really, really ambitious. So trying to have both these things makes it essential to use really more fancy cryptographic primitives, like non-malleable codes, and you restrict the class of attacks. And that's, again, not something that we want. OK, so bottom line, there are works, but they don't seem that they could come in practice anytime soon.
Right? As long as not all of the processors are attacked by a virus, you're fine. Right? This is basically the last bullet.
No, wait, what do you mean?
When you have limited attacks, right, like in the last bullet.
What? The attacks are not limited.
Well, split state is limited.
Yeah, that's what happens here, yeah, of course. Yeah, no. I mean, the general principle is that, absolutely. But you know, you have arguably, it's not clear whether those attacks are all you want to protect against. Okay. And luckily I have some time to go into our results. Okay, so what we provide is a model and definition for virus detection schemes and then an instantiation with the following properties. So we almost did no architectural assumption. Our slowdown factor when the program executes is very, very small, a very small constant. It can be done even smaller by some hardware modification. We make, of course, no timing assumption, so we can interrogate over the internet. We don't need to know the configuration of the system and so on. We don't need secure storage. Our system can secure dynamically updated binaries, so with no cost, no interaction. The verifier does really, really little work. Essentially, it's just one encryption and checking for inequality. Okay, and he has only public information, so no secret keys shared between the verifier and the system. Okay, that's it. Those are all the properties. Okay, and how do we do that? So we're going to use the random access machine model, like the model where the CPU just has the instructions and the registers, and even the program and its data is stored on the RAM. So in this talk, RAM will refer to random access memory, not random access machine. So just to make a bit more confusion. Okay, so we will assume that the RAM executes as usual in fetch then execute cycles. It gets in each cycle it gets a word from the memory. It puts it on a register of the CPU and then performs operation and potentially writes something into the memory. And this is without loss of generality assumption. We assume that the word size is order of the security parameter. This makes sense in modern architectures. We have 128-bit words. 128 is a pretty reasonable security parameter, but we don't need this assumption. Okay, so here's what a virus detection scheme is. It consists of 5 algorithms: key generation, that generates a compilation of verification key, compilation, which takes the software we want to secure and the compilation key and generates a secured version, and then a challenge response protocol. So a challenge algorithm that takes just the verification key and outputs a challenge, a response that takes the software that we secured, or actually whatever it's been computed on it, and the challenge and outputs the response. That's what the system will use, and then the verification, which is a predicate that says whether the system has been attacked or not. And the security is defined via this game. So this is described as a game between an adversary and a challenger. So the first step is to compile the software using the compilation key into a secured version, which we then write into the memory. Then the machine executes, the system executes, and at some point the virus injects, the attacker injects its virus. And before or after this happens, and multiple times, we can do the challenge response protocol, where the verifier, that as I said can be a very lightweight device, generates a challenge, the system produces a response, and the verifier checks using the verification predicate output 0 or 1, depending on if the virus is there or not. So
I have a model question. So does this model cover the case, for example, where the software itself is the one that loads the virus? Like
No. So if you get a pop-up which asks you whether you would like to install a virus and you click yes, we don't protect.
No, you want to install a PDF, and so it downloads a PDF. The PDF has a virus inside.
No, that's what I meant. Yeah, the pop-up will not ask you. So
I just want to understand. So is that
no. It's like buffer overflows. It's type of injections that you don't approve implicitly or explicitly. But it can be combined with other approaches that protect against such. Like you would need certificates there, right? You could check the signature of the thing you're downloading and stuff. You could combine this system with that one. We haven't done it, at least not yet. So such a VDS is secure if it has the following properties. This is kind of a completeness property, compilation correctness, which says that the software which has been compiled computes the same thing as the original software. Verification correctness, which says that if there has not been an injection, then I will not catch one. And soundness, which says that if there has been an injection of malware, I will catch it with overwhelming probability. Okay, and now how do we do it? Evgeny. So we will go in 2 steps. First, we will describe a simple scheme. I have some time, right?
Yeah, 7 minutes.
Okay. First, I will describe a simple scheme which does not need any extra architectural assumptions, but it only protects against a smaller class of attacks. Like I will say what this class is, and then I will show how to make it better to protect against any injection, even if the virus knows exactly the locations where I would put the key shares, even if he is arbitrarily small. For that, we will need some extra architecture, like some microcode piece or something. Okay, so for the simple scheme, the key generation algorithm is a public key encryption key generation algorithm. So the compilation key is the secret key, the verification key is the public key. Now for the compilation, I'm going to use an additive secret sharing. Very, very simple tools. Very fast, but what additive secret sharing is, it just splits a key in many shares that sum up to the key. The very nice privacy properties that it has, if someone has all the key shares, he can recover the key, but even a single share missing information theoretically hides the key. Furthermore, if you overwrite any T bits of any of the shares, you're effectively losing T bits of the key. Right? This is XOR operation. Okay, so and how am I going to use it? Let's assume that this is our entire system memory. And this is the entire memory, apart from the CPU registers, that's the only memory that the system has. That's an abstraction, of course. And assume that it has like 2 n words, and I want to compile a 3 words software in there. So what I'm doing is, first I'm writing these words where I leave an empty word between any 2 of those. And whatever free space it is, I keep doing that, but put no ops. So that this will be kind of working space for the system when it tries to compute, or it could be data in there or anything. Okay, so next I take my secret key, I compute a sharing, let's say that this is the sharing, and then I interleave shares of the key between every 2 words. So finally what I do is, of course, if that software here executes, then it won't compute the same thing as the original, right? Because it needs to go from, if this software would go from, execution would go from W1 to W2, this thing needs to do the same thing. So I'm making sure that this is the case by adding appropriate jumps and making sure that I remap the instructions that point to memory locations to point to the correct memory location. I, of course, cannot do that for an arbitrary binary, but we saw that we can do it for a complete class of binaries, which is, it includes many things, and it's not like just sequential, so it's roughly any non-self-modifying binary. And if I have the source code, I can compile it anyway in such a binary and then compile it in this secured version. If I don't, it's an open question how wide this class can go. Okay, so what's the challenge response? Again, this is the memory. The challenge is I choose a random element and I compute an encryption of it using the verification key. The response, I reconstruct, so the system does that, right? It reconstructs the secret key and then decrypts the challenge, sends it to the verifier, who just checks that it equals with the original random message it shows. So a kind of buggy version, an informal version, or everything that allows me to make a wrong claim is that if the injection overwrites 2 consecutive words, then it's caught with high probability. And the proof of the buggy version is that if you overwrite 2 consecutive words, then you inevitably overwrite the key share, which means that you destroy the key. Okay? So something which I did not discuss is, of course, that I want the system to be able to reply to the challenge, right? So this means that the system itself, so the code that is running, should have the response code in it. So before I even start compiling, what I do is I add the response code and then I compile the entire thing. So this way I protect also the response code. And what properties do I get from that? As I said, it's a very simple version, no architectural assumptions. The performance, we do pay kind of, that's a very bad overestimate, but to add the keys in between and the jumps, you pay 3 times the space. We don't really pay 3 times the space because most of the jumps are already there, and you can have a word which has instruction and a jump. But this is a bad overestimate. But we don't really care that much about it. What we care is time, because space is a much cheaper commodity nowadays. And in terms of time, the slowdown comes only from the extra jumps. So when the system executes, it ignores completely the keys, it jumps over the keys, and the only slowdown is for these jumps. When the system is interrogated, then it needs to traverse the entire memory, and it needs to, but when it traverses, it doesn't do anything fancy, right? It just does an XOR of the words that it reads, and then it does a single decryption. So this thing will take a lot of time, well, I don't know, minutes, but you have the guarantee that you will be able to catch any injection in a minute or in 10 minutes versus not being able to catch it, and you won't have any slowdown in your execution. So we believe it's better than the state of the art, which is like not catching it. Okay, and the verification, as I said, just choose a random message and encrypts and checks for equality. So that's all it does. So I still haven't answered completely Moti's question, and I'm going to do that now. The reason why I said that the theorem was buggy, informal because it was informal, but buggy is because of what is known as a time of check, time of use attack. And this is exactly what happens if I attack the verification, right? So in other words, I have my program which is secured, it's executing, and while it's executing, it hasn't been attacked yet, a challenge comes in. What does the system do? It starts reconstructing, it reconstructs the secret key, and now it's about to decrypt, or it starts decrypting. So assume that at that point exactly, the virus attacks. Evgeny went and bought this thing like off the shelf, right? Wow. Wow.
This is what happened to Evgeny's laptop.
Okay, so assume that now, while it's executing and it has the key reconstructed the memory, now the virus attacks, right? I'm attacking this process. That's a disaster. He just sits anywhere he wants, does anything he wants with the system, and just uses the key that is on the CPU anyway to reply, and it replies any future attempt. How do we solve that? We use two keepers, SK1, BK1, SK2, BK2, in tandem. What I mean by that is that we essentially interleave the sharing. So we put first word, first share of the first key, first share of the second key, second word, and so on and so forth. And then the challenge is a double encryption. First we encrypt with PK2, then we encrypt with PK1, and that's the challenge. And we expect the system to decrypt both. How? First, it reconstructs the second key. The first key. It strips off this encryption. Then it erases the data where this first key was stored. Then it reconstructs the second key, strips off the second encryption, and replies. So the now non-buggy, but still informal version of the theorem is that if the injection overwrites two consecutive words, then it's caught with high probability at the latest in the next verification. Why? If it overwrites again two words, what it will have to do is kill one of the shares of the two keys, right? And either this key has already been reconstructed, so that does not affect it in the current attestation, but it will be caught in the next one. Or it hasn't been used yet and we catch him on the spot. Actually, by just using 2 hashes of the memory, we can catch him on the spot without waiting for the next attestation. I won't discuss exactly that. I'm happy to discuss it if someone's interested. Okay, so, I'm out of time? Okay, so very quickly, how can we kind of improve that to allow the virus to know exactly where the keys are stored and install just small, a couple of bits everywhere. So instead of spreading, we spread by one word more. Then we put our secret keys as before in tandem, and we also, in this word that is there, we put a special MAC, which consists of 2 hashing of the keys and then a multiplication and addition. And to take advantage of the MAC, we assume that the architecture itself is slightly stronger. So instead of just taking one word at a time, it takes 4 words, first checks the MAC, and if the MAC verifies, it goes on and processes the word. Otherwise, it just overwrites the part that it just read. And This is an informal theorem which says that any injection now will be caught with high probability. And the idea is that the MAC and the proof guarantee that if I override small parts of the key, I won't be able to guess the MAC. I will be caught just by the MAC check. If I override large part of the key, I will be caught by the attestation because I'm missing a large part of the key. Of course, here I need the encryption scheme that is used to be leakage resilient because I'm not overriding everything. So that was very fast, sorry. Okay, so the properties that we have I won't go through. So the slowdown is essentially the jumps and the MAC. And the MAC could be potentially done in hardware. Hopefully we will do it soon. So just the point here is that modern CPUs already do these operations that we need for the Mac and very efficiently, like field addition, field multiplication, and hashing. That's all we need. And the verification is roughly the same, but the encryption algorithm is heavier. Okay, so concluding. This is just the beginning, so there are like tons of questions. I'm sure that you have even more. One is, of course, we are very wasteful in terms of memory. We would like to be able to compile more programs this way. How can we design the CPU so that it really minimize the slowdown from this extra MAC instruction? The big question is, this is a very simplified version, so how can we extend it by having secondary storage and exchange there? And of course, the obvious next step is simulations, implementations, and benchmarking. And with that, I want to thank you and thank Hugo for not being very
Okay, some questions.
I didn't understand how this accommodates viruses that inject themselves onto the stack.
So we take the memory includes everything. So what I have, that's this vector of the. So this memory includes the stack.
So the stack can't be used for your secret shares.
As is now, it can. So it doesn't fit that simplification for now. But the next step is to try to extend this. This is a very simplified model, right? Have a unified memory stack.
These programs need to have state somewhere. Just in general, what happens with the state? Some of the memory needs to be used for the program.
Yeah, the green parts of the memory are for the program only. They're not touched by the attestation. So you can think. So the stack is supposed to be on these green parts of the memory. Yeah, everything, all the useful memory that you're going to be having. The W's, yeah, wherever the W's are. This is where the program is. This is like.
If the virus injects itself there.
Then we will catch him because of the MAC.
The MAC covers the.
Yeah. The previous word.
Every time you update the stack, then you have to recompute the MAC.
Yeah.
Better to get incremental.
There's like a lot of things, optimizations that can and should be played there. Yeah.
One more question, or two questions and one answer.
Okay, one.
So does the adversary get to see the contents of memory before he injects, or is he somehow oblivious to?
He doesn't get to see the keys or the key shares, obviously, but he knows he can even choose the software to be compiled. And he knows the exact compiler, so the compiler doesn't use anything about it. So. Have another question and no answer? Or?
No, so
okay.
Thank you again.